So as I said, this 1 kilo ohm and 4 nanovolts per root hertz is a good number to keep in mind, right? And also gives you an idea of what these numbers are like. Okay, good. All right. Now let me give you another. Let me ask you about. So let us say this is simply an amplifier with a gain A. Correct? What comment can you make about the mean square value of the noise now? If this voltage is Vn, what do you think? The voltage here will be A times Vn. So, what comment can you make about the mean square value of the output? This is simply will be A square times, correct? All right. So, that was easy. Now, the next thing, if this was a noise voltage source with a spectral density SVN SV of f, what comment can we make about the spectral density of the noise here? Pardon? This is simply nothing but A square times the spectral density of the noise, input noise. Easy enough? All right. Okay. Now, let us say I have a filter here with a transfer function h of f. I have a noise source. I mean, though I keep marking plus and minus, right? I mean, remember that the mean is 0, so it does not really matter. SV of f. What comment can we make about the noise spectral density here? Remember, what is SV of f? It is simply, let us say that this noise spectral density is doing something like this. Okay. The noise spectral density, remember, quantifies at a certain frequency f, and if you have a bandwidth of delta f and this is f, all right. The mean square noise is what? Here in that bandwidth, what is it? Yes, SV of f times delta f. So, that is the mean square noise in that band, correct, centered at f. Now, what is the gain of the filter at a frequency f? Mod h of f, correct. So, this is getting this spectral density is being passed through an amplifier whose gain is dependent on frequency, and at a certain frequency f, the gain of that amplifier is h of f. So, what comment can you make about the spectral density at the output, or the mean square noise at the output at a frequency f? Do you understand the question? At a frequency f, the mean square noise here will be SV of f times delta f. Okay? And earlier when we had an amplifier whose gain did not change with frequency, all of you immediately said that the spectral density is basically at the output is A square times SV of f. Now, what do we need to do? Well, the gain is changing with frequency. This consists of components at a frequency f, right, and a narrow bandwidth delta f. The gain corresponding to that frequency is h of f. So, what comment can you make about the mean square noise of the waveform coming out at frequency f? Very good. It is simply, so therefore, the output noise spectral density is simply mod h of f the whole square times SV. right. This is also very straightforward. Okay. So, this is what comment can you make about if you have a noise source with spectral density SV of f, what comment can we make about the mean square noise of the noise source? In other words, if I put a filter there whose bandwidth is infinite, what do you expect the mean square noise to be? Well, remember that the mean square noise, if you put a band pass filter of bandwidth 1 hertz or delta f hertz, is SVFF times delta f, correct. So, if I put a filter with the bandwidth, if I do not put a filter at all, what would be the total mean square noise? It is simply nothing but, well, it is the mean square value of this component plus the mean square value of that guy plus the mean square value of this chap and so on. So, this is nothing but integral SV of f df from 0 to, all right. Okay. So, all right. Okay. Now we just put everything together that we have seen together. So, well, let us say you have a noise source with a noise spectral density SV of f. This is H of f. What is the output? What is the mean square output noise? What is the output noise spectral density? Pardon? Mod H of f times SV of f. So, what is the mean square output noise? Integral 0 to infinity mod H of f the whole square times SV of f. Does it make sense, people? Right? As you can see, all this, I mean, the random process guys will will throw a fit if they see derivations like this. But if we have to sit and do stochastic processes and do this, I mean, by the time we build our circuits, we'll be dead, right? So, okay. So, these seem intuitively reasonable, okay, and this is what we are going to use. This is good enough for us to make useful calculations like the one we will do right now. Okay. So, let us start applying the stuff that we have seen to real circuits. So, basically every resistor is accompanied by a noise source. The bottom line is that every resistor is accompanied by a noise source whose noise spectral density is 4 kT R volt square per hertz. You can think of it as as there being a voltage. So, I mean, there is a voltage source in series with every resistor and the noise spectral density of that voltage source is this. Now, let us try and see if we can make some calculations. So, this is, let us take our first simple circuit. This is a resistor and a capacitor in parallel, right. So, this is Vn, this is a voltage source, right. Okay, it just happens to be a noise voltage source. So, if this is a voltage source, what comment can you make about the transfer function from the voltage source? We are interested in finding the noise spectral density at the output as well as the total mean square noise at the output. So, how do you propose that we go and find out the noise spectral density at the output? So, we want to find SVO of F and find the mean square noise. So, how do you propose that we find SVO of F? Well, that voltage Vn is there. There is an RC filter. So, what comment can you make about the transfer function from Vn to Vo? So, the transfer function H of F is 1 over 1 plus J 2 pi FRC. So, the output spectral density is the mod H of F the whole square times the input spectral density. The input spectral density is nothing but 4 kT R, alright, times, what should we do? 1 over divided by 1 plus 4 pi square F square R square C square. Okay. And how does this look? What will the spectral density be at DC? Okay. At DC it will be 4 kT R, and why does that make intuitive sense? At DC the capacitor is open, the transfer function is 1, so the low frequency output noise spectral density will be the same as that of the input. And why does this shape make sense? Well, it is a low pass filter, right? At high frequencies the capacitor is behaving like a short. So, the high frequency components of the noise are getting attenuated by the filter, and that is what the filter is supposed to do. Alright, so that is clear. Now, the next thing is to find the mean square noise at the output, the total mean square noise at the output. And how will you figure that out? Well, it is simply 4 kT R integral 0 to infinity 1 over 1 plus 4 pi square F square R square C square dF. Okay. And well, you use 2 pi FRC as U, and dF is nothing but du by 2 pi RC. So, this is nothing but 4 kT R over 2 pi RC integral 0 to infinity du by 1 plus u square. So, I don't know how many of you still remember the integral. What is it? And was u, alright, and that has to be evaluated between limits of 0 and infinity, which basically is, what is that? Pi over 2. So, the mean square noise after all this is 4 kT R times pi over 2, just like in your JEE or GATE exam. All the everything cancels out, 2, 2, 4, R. What do you get? KT by. Alright. So, what is this telling us? That the mean square noise is all important quantity KT over C. Now, we kind of little bit puzzled. I mean, this integral seems pretty complicated, right? Perhaps we made a mistake. How is it possible that the mean square noise is? I mean, after all, the noise is coming from where? From the resistor, and but the total integrated noise has got no R in it at all, right? I mean, that would sound to me like, oops, maybe we made a mistake, right? But then I trust your judgment on, and I trust your competence with integral calculus, so it appears right. So kT by C. So now we got to figure out. Well, the answer, turns out to be kT by C. Why does this make sense? Right? One thing can say, what can I say? It comes out of the math, right? Okay. The question is there, some intuition behind this design, right? So, as you can see, if I reduce the resistor, what is happening to the spectral density of the noise produced by the resistor? Let us say we reduce the resistor by a factor of 2. What happens? Oh, well, the noise added by the resistor is smaller. I mean, the spectral density of the noise added by the resistor is small, right? But there is another important thing happening. What's that? Oh, well. Right? The bandwidth has become wider, right? The spectral density has gone down by a factor. Let's say I reduce the resistance by a factor of 2. What has happened to the spectral density of the resistor? Of the noise? This has gone down by a factor of 2. Oh, but what has happened to the bandwidth? Oh, well, the bandwidth has also gone up by a factor of. Alright. So, while it is true that reducing the resistor has the beneficial effect of reducing spectral density of the noise source, well, the total noise, does not change because, the bandwidth over which it makes a contribution is now larger, right? Now, that does not mean that this factor and that factor exactly cancel. In this case, it just so turns out that, the reduction in spectral density exactly cancels out the increased bandwidth. Does it make sense? Right? So, that is the intuition behind this kT by C. Alright. So, now all of you look sufficiently bored, how about doing this? This is C1, this is C2, this is R1, this is R2, right? And of course, we are not going to do this in the class. Alright. So, okay. So, you have two resistors, so you have two noise sources, and let us say we are interested in finding the mean square noise across. We are interested in finding the spectral density and the mean square noise across C. Okay. What are we going to do? Nothing fantastically new, right? What do? We need to find the transfer function from Vn1 to the output, let us call that H1, the transfer function from Vn2 to the output, let us call that H2, alright. And so, what will be the what will be the noise spectral density at the output? What is the noise spectral density at the output? Can I get a clear answer? So, the spectral density of Vn1 is 4 kT R1 times mod H1 of f the whole square plus 4 kT R2 mod H2 of f the whole square. Right? We are adding powers, okay. That is only true if the cross terms, right, are, see, Vn1 will result in some output noise here. Vn2 will result in some other output noise waveform. Okay, and what we are saying is that the mean square noise of the sum is the same as the sum of the mean square noise of the individual components. That's only true if average value of Vn1 of t times Vn2 of t, this average is okay, and that it turns out that is indeed true. Physically it is because, well, this noise is because of random movement of carriers in the resistor, in the conductor, right. There is no way carriers in one conductor can know what's happening in the other conductor, right. So it's like saying, if you have a whole bunch of classrooms, right, every class is noisy, right, but the noise in one class is completely unrelated to the noise that's happening in another class, because different people are sitting there, hopefully yakking about different subjects, right. So what you hear is basically no correlation between that, and these are independent. Okay, so that's very convenient, because all that we need to do is we need to find the transfer function from these noise sources to the output. I mean, you're already experts at doing this, because you can write the M&A matrices and boom, correct? And then once you find the transfer functions, you basically find their modulus square, and then you integrate, and then you're done, right? So if you have 400 resistors and 300 capacitors, what will you do? Well, the same thing, 400 times, correct? Okay, so you need to find. So this is where if you want to find the mean square noise of the output of the network, you can see now that you need to find transfer functions from multiple input sources to the same output, right? And this, as you know, I mean, if you could do this by superposition, right? And that's as we've seen, it takes a very long time, simply because you are doing the same old calculations over and over again. So what what do you, now that you know everything about reciprocity and adjoints, what do you think you will do? Why do you think those concepts are useful? To find H1 and H2 and H300, you don't need to do it one source at a time. You just excite the output with the current source and evaluate the whole network just once and find the currents through all the individual voltages, right? Okay.